Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at approximating the solution to a quadratic equation. That is, finding the two roots. So in this topic we will consider finding the solution to the quadratic equation. We will see how the techniques you saw in secondary school work with extreme cases. And unfortunately, these extreme cases tend to be quite common. Therefore, we will consider alternative techniques for finding these roots. All right, you should think, this is easy. Here's the quadratic equation. And of course, you know what the roots are. Let's try this in MATLAB. So suppose we have the polynomial 0.0002 times x squared plus 57,023 times x plus 0.000001. Now, these are the two actual roots to the number of displayed decimal places. Let's see how MATLAB does. And remember, MATLAB is using double precision floating point arithmetic. So it doesn't matter whether or not you're doing it in MATLAB or in C++, you're going to get the exact same result. So let's calculate the formula for the one root. Well, taking a look at that, that's actually pretty good. In fact, to 16 significant digits, it's actually very accurate. Let's calculate the other root. So now it's negative b plus the square root of the discriminant. 0. Well, the actual solution, if you look up there, can quite easily be represented as a double precision floating point number. So 0 has essentially 100% relative error. That's not a very good approximation. So what happened on that last slide? Well, here is the formula for one of the roots of the quadratic equation. However, what happens if b squared is much larger than 4ac? In that case, b squared minus 4ac is approximately equal to just b squared. So now the formula simplifies to that. But that's just equal to negative b plus the absolute value of b. And if b is positive, then that works out to 0. Not a good approximation. All right, can we find an alternative form? Well, let's rationalize the numerator. Rationalize the numerator? Well, yeah. So let's just multiply both the numerator and the denominator by the radical conjugate of the numerator. So we're multiplying by 1. Expanding that out gives us this formula here, which can be simplified and thus further simplified to be this formula here. Actually, normally we write it as follows. So here are two roots or formulas for the two roots that give us the exact same roots as the original quadratic formula. Well, let's try this new formula in MATLAB. Again, here are the coefficients of ax squared plus bx plus c. And these are the two actual roots. Well, let's plug this in and get the smaller of the two roots this time. Well, That's actually pretty accurate. All right, so let's try the larger of the two roots. Oh dear, that's worse than 100% relative error. That's an infinite percent relative error. Okay, so now we have two formulas for finding the roots of a quadratic equation. One which seems to be reasonably good at giving us the larger of the two roots, and the other appears to be better at giving us the smaller of the two roots. Larger and smaller in absolute value. So therefore, the formula you learned in secondary school so well is actually only really useful for finding the larger root in absolute value. We now have an alternative formula that is best for finding the smaller root in absolute value. All right, so if b is greater than 0, then b plus the absolute value of b is equal to 2b. Therefore, the formula for finding the larger root will be negative b minus the square root of the discriminant all over 2a, because negative b is negative, and if we subtract a negative number from a negative number, we are not going to end up with subtractive cancellation. Alternatively, if b is greater than 0, then b plus the square root of the discriminant is going to be a positive number plus another positive number, which will make the denominator a very large positive number, which will therefore give us the smaller of the two roots using the formula on the right. On the other hand, if b is negative, then negative b will be positive. Positive plus the square root of the discriminant is going to be a formula not subject to subtractive cancellation, and that will once again give us the larger of the two roots. And again, in the denominator, if b is less than 0, then b minus a positive number once again is not going to be subject to subtractive cancellation, and therefore will give us the smaller of the two roots. Let's actually implement a function to return the roots of a quadratic equation. The arguments will be a, b, and c, which will be assigned to the parameters. And these will be the coefficients of x squared, x, and the constant coefficient respectively. We will return a standard pair of two doubles. This is a very simple data structure that has two public member variables, first and second, which is implemented in the utility library in the standard template library. So in this function, the first thing we will do is assert that a is non-zero, otherwise we don't actually have a quadratic equation. Next, if b is equal to 0, then we're just going to check if negative a times c is greater than or equal to 0. That is, we check that a and c have opposite signs. And if this is true, then we can easily calculate the two roots as seen here. Otherwise, let us assert that b squared is greater than or equal to 4ac. Otherwise, we have imaginary roots, and that is not what we're discussing here. We're looking for two real roots, and thus this must be true. Therefore, if that's true, we will assign to the discriminant local variable the square root of b squared minus 4ac. Now we check. If b is greater than 0, we will return these two roots. Otherwise, b is less than 0, in which case we return the two alternative formulas. Following this topic, you have now reviewed the quadratic formula, and you thought this would be easy. However, you now understand that the quadratic formula is not always the ideal formula to be used numerically. This is because the numerator is potentially subject to subtractive cancellation. You are aware that there's an alternative formula that works when the standard formula does not, and you have seen an implementation that correctly returns both roots to the maximal precision that can be reasonably considered possible. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!